Good morning, everyone. Welcome back. Thanks for joining us. We're glad that you're here. I'm Steve.
And I'm Scott. And you're kind of distorted.
Oops, sorry.
Probably should have noticed that before.
Can you see me clearly now? No? Let's try.
You're like elongated.
There we go.
Perfect.
We're backyard musings.
Sorry.
Both of us.
Yeah. He's Steve and I'm Scott.
Right. Okay.
And today we're talking about quantum states.
Which Steve loves.
Steve loves the quantum. Yeah, he's all about it.
Really interesting. I mean, I think it's fascinating. Researchers have shown that an unusual quantum state known as a fractional Fermi Sea, F-E-R-M-I-C, can be deliberately created, opening the door to a previously unknown phase of matter. So I think phases of matter would be solid, liquid, gas, and now Fermi Sea. The work, published in Physical Review Letters on June 9th of this year, was carried out by Nägerl Group, together with theoretical collaborator Alvise Bastianello of the CNRS and Université Paris-Dauphine. Dauphine is princess. The study provides the theoretical foundation for recent experimental work led by Hans-Christoph Nägerl's group in the Department of Experimental Physics. Woo! Would you like to know more? Hopefully you do.
Okay, the team focused on ultra-cold cesium atoms, cesium atoms, confined to a single dimension. By repeatedly changing how strongly the atoms interacted, cycling between them, or between strong repulsion and strong attraction, they pushed the system far from its normal equilibrium state. Rather than behaving according to the well-established Tomonaga Luttinger liquid theory, which we all know that theory, right?
Of course.
Yeah, entered an entirely new critical phase of matter.
Groundbreaking theory.
Okay.
This newly predictive phase arises through a process called quantum engineering, showing that carefully controlled interaction cycles can produce forms of quantum matter that do not occur naturally under ordinary conditions.
Okay, Steve, I know you already know this, but I'm going to repeat it anyway. At extremely low temperatures, quantum particles normally arrange themselves according to well-defined rules. Is that Alvise Bastianello explains. Fermions, for instance, whatever they are, stack linearly into the available energy states to form the so-called Fermi Sea. But what happens if one forces interacting atoms to continuously cycle through extreme conditions, smoothly shifting them from strongly repelling each other to strongly attracting each other? Kind of like humans.
I want to know what happens. I'm like nail biting right now.
This is like a quantum atom soap opera.
Yes. The researchers found that this carefully designed interaction cycle drives atoms from their ground state into a highly excited, yet surprisingly organized non-equilibrium state. And I mean, just thinking about it, when it's not in equilibrium, it's bouncing all around, right? They call this unusual arrangement a fractional Fermi Sea, because the particles appear to obey a reduced occupancy rule.
Okay. Quote, instead of simply heating the system, the interaction cycle reorganizes the atoms into a new many-body state. And that's according to Yi Zheng, the study's lead author. Going on with a quote from Yi, this gives us a controlled way to explore quantum matter beyond the usual equilibrium paradigms.
Okay. The fractional Fermi Sea displays several distinctive features. Mathematical relationships between the particles produce pronounced ripples known as Friedel oscillations. Oh my gosh. Wow. Along with characteristic decay patterns across all levels of repulsive interaction. Wow.
These signatures clearly separate the new state from Tominaga Ledinger or Ledinger liquids, which have long served as a standard framework for describing one-dimensional quantum systems. Quote, this state is highly excited, but it is not random, says Hans-Christoph Nägerl, the group's leader. It has a hidden order, going on with the quote, it has a hidden order that becomes visible in its correlations. He adds, we are not yet sure how we should name these new quasi-particles, perhaps super fermions.
Wow. If there's, folks, I'm just going to interject. If there's one thing you take away from this article, it's this. Tominaga. The unique behavior of fractional Fermi seas points to an entirely new exotic critical phase of matter and provides researchers with a new way to investigate universal quantum behavior using cold atom simulators.
As Nägerl explains, and I'm probably butchering that name, so I apologize. Quote, the discovery of fractional Fermi seas shows how far we can push quantum simulation, not only reproducing known models, but creating and probing states that go beyond the established paradigms.
A companion paper describing the experimental realization of fractional Fermi seas through quantum simulation is currently under review. Okay.
Okay, wasn't there a character in a show or a toy or something called a Fermi? Maybe not.
No.
Squirmy, maybe I'm thinking of. It's kind of a furry thing. Anyway.
What does this all mean? What does it mean?
I have no idea, to take a quote from one of my grandsons.
Well, if you're a physicist, put something in the comments to break it down even more for us.
Yeah, let us know to further explain how stupid I am when it comes to this kind of stuff. But Steve is all over quantum. Whatever quantum it is, he is all over it.
Just because of the Tominaga. All right, folks. Thanks for joining us. We'll catch you this afternoon.
Take care. Have a good morning.